Properties of that trigonometric function. One of the things that we have to determine whether is domain and range. It's always a good thing to know what numbers we can put in and obviously what numbers can come out of this. Now, when you take a look at the domain of the sine and the cosine, I can put any number in that I want. Doesn't matter. I will get something back out again. Now, obviously, when we take a look at tangent, because we've got it as y over x, we've got a big problem there when either value x or y for tangent and cotangent is going to be 0. Likewise for cosecant and secant. So we need to be aware that we are going to have points of discontinuity when we are dealing with these things. Okay? Just simply undefined. We don't know what we're going to get. So now, the domain of a tangent function is always going to be on this idea of multiples of pi over 2. If we think about this in terms of the unit circle, when we're looking at sine over cosine, and cosine being x, wherever x is 0, we're going to have a problem. So every time that I hit here, every time that I hit over here, I get a 0, and every time that I hit up here, I get a division by 0 error. So at 90 degrees, it's going to be undefined. Likewise down here at 270, it becomes undefined because you're putting in x is 0. And that just simply doesn't work for us. So now the other thing is when we take a look at the ranges, what possible values are we going to get out? Well, let's go back here. What's our largest values? The negative one. I mean, those are only the values we're going to be getting out of this thing, right? We can't get a number for x larger than 1. We cannot get a value for x smaller than negative 1. That's just the way it is. Likewise for the y. Can't go above 1. Can't go below negative 1. This is what it's going to be. So now when we get to cosecant and secant, things get a little stranger. Because cosecant is going to be less than negative 1 and greater than 1. Remember, cosecant is the inverse of which one? So it's a 1 over operation. Now, quite often it is kind of difficult to understand what is going on with that when we're looking at just this unit circle. So what I want you to do, grab your graphing calculator. And this is going to give us a better idea about what's happening with it. Now I'm going to do a setup on here, and now mind you, this is going to move us into a shades of trigonometry here that they're based on the unit circle, but it's another way to look at the graphs on this stuff. And we'll be going into this more in depth as we go, but what I want you to do first, go to mode, make sure that we are in radians. Good. Window. What we're going to do is we're going to set the window so that we're only seeing what the values will be for the unit circle. So what I'm going to do here is I want to set this here at negative 2 pi. So this is going to go from negative 2 pi over to 2 Now don't worry that it goes and puts it into a decimal, that it understands what's going on with it. Now, scale, we're just going to leave that, we're not going to leave this as 1. I can set the scale up to be as pi divided by 2. So now we're going to be thinking about this in terms of the trigonometry and what we're going to have for domains and ranges. Now I'm going to set this for -2, and I'm going to set this for 1 and 2 here for the y minimum maximum. And I'm just going to leave the scale at 1. The reason why I want to do that is so that we're able to see what's going on with the inverse functions, cotangent, cosecant, secant. So now let's go up to y equals, and I want you to put in sine. Graph it out. And it says go to. What did I forget to put in there? Well, probably an X would be helpful, right? Graph. Right? So I see this going on. You've seen these things before, but this is what a sine wave is. If I graph it out on a coordinate system as I go around the unit circle, this is what I see. So if I start at 0 pi, I go up maximum 1, values come down, and it goes back up, periodic function. Now, what does cosine look like? Let's go to y equals. Let's put in cosine. I'm going to put in the x. I graph. Okay. So there's sine, there's cosine. Now, let's take a look at tangent. See how it compares. If I put the tangent of x in there, I get this. Okay? A little messy. Let's go back in and let's clear out the sine, clear out the cosine, and just look at what tangent is again. Okay. So, if I go and put a trace on this, and I tell it that I want it at 0, we got that. 0 is 0. What happens if I put in pi? What is it doing at pi? Well, it's at 0 again. These are things that we expect. What happens if I put in pi divided by 2? I don't get anything, do I? Because the denominator, as it is approaching pi over 2, as it approaches pi over 2, x is tending towards 0, correct? And we know that as a denominator approaches 0, that the numbers get really super huge because we're dividing by that decimal again, dividing by that fraction, making larger values for it. So this is what is happening here. That's why you see. Now it's got a repeating pattern onto it. And if you want to, you can take your window and say move out to -100 and 100 on the y. Graph them out. Okay. You've got your asymptotes. It only goes up so far, and then it goes and has problems with it. Okay. I suppose if you wanted to see it, maybe at from -10 to 10 might give a little bit better definition for you, because then you can see the curves that are going on with it. But you definitely get the picture that it's getting to that value and doing that. So, what about secant and cosecant? Okay. So, let's go back to y equals. Now, somebody had asked me about this last week, if the inverses that were on here on the graphing calculator were the cosecant, secant, and cotangent, and no, it's not. The inverses allow you to be given a radian measure and figure out what the x was that was put into it. So you put in, or actually, put in something for x, you get out something for y. The inverse gives you something for x when you put in y. We'll get to that a little later. So if I want to go through and do the one that the inverse of this one, and by the way, which one goes a sine? Cosecant or secant? Co. So if I want to graph the cosecant, what I would do is parenthesis 1 divided by sine of x. Close it and close it. So now look at what happens when we graph. Okay. And I did leave it on that 10. So there's my sine waves. And now here comes the cosecants. Again, we've got this problem if we hit the trace and I go to pi divided by 2. I get this. So I've got it down there. That's great. But as we approach going to the left or to the right, it's going to become undefined. So if I put in 0, I get that. Oh, I'm on the wrong one, sorry. There we go. 0, undefined. Okay. If I put in pi, undefined. Well, again, if sine is supposed to be our y, when we put in 0 or we put in pi, that's when y approaches 0. That's where we should see our points of discontinuity. So if we go back again and take a look at this with cosine, so put in the cosine there, put in the cosine there, and we hit graph, we see that this one is going to be the same kind of an idea, and we can identify where the points of discontinuity are again. So trace, move up to that, and here if I hit it at pi divided by 2, that's e divided by 2, that was a bad idea. Pi, there we go. Pi divided by 2, what do I get? Absolutely nothing. Why? Because as cosine approaches 0, 1 over cosine is going to become undefined. But this way of visualizing it helps out a lot more than what you see here on the unit circle. You have to be able to go back and forth and coordinate these two graphs. So that chart there, kind of summarizes what we've been all talking about here. Now, next thing, period. When we're talking about these type of functions, these are periodic functions. In other words, they repeat over and over and over and over and over and over and over. So when we look at this, we got sine plus 2 pi k. Sine has a period of 2 pi. It repeats every 2 pi. Now, how can we determine if something is periodic? Well, we get down here, if I have f of theta plus p is equal to f of theta, we've got something going on there. In other words, if I add a certain amount to it, whether it be a pi, whether it be a 2 pi, pi over 2, whatever, you want to add to it to increase it again. Maybe it's just going to be 1, maybe it's going to be a 2. We don't know. But something can be added to the radian measure such that you get the same thing with what was added and what it was originally. That's all it's talking about. So, periodic properties. Another little thing for that wonderful sheet of paper that you've got there. Sine and cosine, you add 2 pi, you get back to where you started from. Tangent, you just add a pi. Cosecant and secant, you add a 2 pi. Cotangent, you simply add a pi. So, we kind of talked about this last week when we were looking at how many times we would round things. So, let's say that I want to find the exact values of these things. here. So I want to find the exact value of whatever this is. What I want to do is I want to take out how many times it goes around. Now, we've got a denominator of 4 here. Okay. What was the period for this? Sine is 2 pi, correct? So that means I would have to have 8 pi over 4. Would that give me 2 pi? So if I've got 17 pi over 4 and I take off an 8 pi over 4, what am I left with? Well, that would be 9 pi over 4. Can I take out another one? So if I take off another 8 pi over 4, I am left with pi over 4. So I go here, we're dealing with sine. Sine of pi over 4 is going to be square root 2 over 2. Okay, that's it. Oops. What about cosine? 5 pi. Well, it's not a fraction there, so I can take off, if I take off a 2 pi, I am left with 3 pi. Can I take off another 2 pi? Yep, I'm left with pi. So what's the cosine of pi? Go back here. Cosine of pi, pi is right here, so the cosine of pi would be equal to -1. Tangent, 5 pi over 4. Okay. Now, is 5 pi over 4 a multiple? In other words, is it possible for me to find 5 pi over 4 on the unit circle? And the answer is yes. 5 pi over 4? 5 pi over 4 is right here, which is going to be 1. Why? Because tangent is sine over cosine, -2 divided by 2, -2 divided by 2. Now, what was the period for pi? Or if not for pi, but for tangent? Gave you the answer, it was pi. So if I take a look up over here and go back a full pi, which is just going to be 4 pi over 4, I get pi over 4, which is 2 pi over 2 pi, which is what? 1. So because it has a period of pi, I can subtract off 4 pi over 4. I would be left with 1 pi over 4, just pi over 4, which gives me the value of negative, or square root 2 over 2, square root 2 over 2, which is 1, and same thing down here. So it repeats itself every pi. Stunned silence. Questions about that by chance? Okay, so yeah, when we're asking for the period of repetition, what does it repeat on? Okay, for example, the school day repeats every period repeats every 50 minutes. So every 50 minutes you change class, you go to another thing. Okay, so we've got that type of repetition. Your favorite show shows up on TV on Monday nights at 8 o'clock. So every Monday night at 8 o'clock, you know what your favorite show is going to be on. That's the period of repetition. So determine the signs. Now, here is one thing that you can go through and add on to this. Oops, delete this page. So when you are here, sine, cosine, Are they going to be positive or are they going to be negative? When we are dealing with quadrant 1, this is going to be, let's see, this is going to be plus, comma, plus. So if I am looking for anything that is going to be positive for sine and cosine, they're going to be over here. This is going to be negative, comma, plus. Okay. This is going to be negative, comma, negative. This over here is going to be plus, comma, negative. Why is this going to be important for us? Well, when I was asked about, the tangent of 5 pi over 4, which quadrant is that thing going to land in? Well, it's going to land in the third quadrant. Granted, we know that its value is going to have a period of pi, so we know we get 1 and we get 1. This is important for us to know, especially when we start working towards saying, okay, what's the radian measure for tangent equal to 1? Two different places it can be. If I ask you for what is the radian measure of sine equal half? Sine is what? Sine is y. So that means it can be one of two quadrants. It's either going to be in the first or the second quadrant. So knowing where your signs are helps dictate where you got to go to look and find the information. Okay. So reciprocal identities. We talked about this last time. Again, just make sure that you have these there so that you know which ones you're looking for. So here we go. We are going to go through and do this. Let's save this one. And grab this. So I am told that sine is equal to 5 pi, or square root of 5 over 5, and cosine is equal to 2 square root 5 over 5. Find the exact values of the 4 remaining trig functions. Now, is there anything on this? And the answer is no. We don't have fifths on here whatsoever. Could we come up with them? Sure we could. Are we going to? No. So, first offhand here, tangent. Tangent is sine over cosine, so that's going to be square root 5 over 5 divided by 2 square root 5 over 5. Okay. So, you'll get used to this trick here. Multiply by the reciprocal, 5 over 2 square root 5. Cannot divide by a fraction, multiply by the reciprocals. 5's cancel square root 5 here, so that means that the tangent of theta is equal to 1/2. That's what it is. Okay. Now, that also means that the cotangent is equal to what? Well, that would be 1 over tangent, right? But since it's 1 over tangent, and tangent is half, that means it should be equal to what? 2. So in this case, cotangent of theta is going to be equal to 2. So, as we go back and we take a look at what they've given us here, again, cosecant and sine, secant and cosine. They're opposite each other for the letters if you can't remember which ones are which. So if I want the cosecant, that's going to be equal to 1 over sine. You're going to multiply by its reciprocal. So what's the reciprocal there? 5 over square root 5. Now, here's a little bit of a problem. This is basically a style format problem. In mathematics, we do not like to have radicals in the denominator, so we have to rationalize them. So whatever radical is in the bottom, we multiply the top and the bottom by it. It's just 1. So cosecant here is going to be 5 square root 5 over 5, right? But these 5's can cancel, so this is just going to be square root 5. That's it. Secant is going to be equal to the reciprocal of that, which is going to be 5 over 2 square root 5. Multiply again by the square root of 5 over the square root of 5. So that gives us 5 square root 5 over 2 times 5. 5's cancel, so this turns out to be the square root of 5 over 2. It's not a bad thing to do, but you have to understand that we are always going to keep things in terms of exact measures. So, what else we got here? Now, fundamental identities, and these little things that are right up on over here. So, cosine squared plus sine squared is equal to 1. Now, let's go back to the unit circle. If I take a look at what's going on here in first quadrant, we had said that x measures cosine. So x this way. Sine is y. Sine measures up and down. So it's this far and that far. So the distance here is square root 2. Distance up here is square root 2, gets us at a 45-degree angle. Pythagorean theorem, folks. A squared plus b squared is equal to c squared. If we know that the unit circle is going to be c of 1, that's how we figured out all of this other stuff. So, sine squared plus cosine squared is going to be equal to 1. Doesn't matter what you've got. Sine squared theta plus cosine squared theta gets us 1. Tangent squared plus 1 is equal to secant squared. Cotangent squared plus 1 is equal to cosecant squared. Have these written down. You need to be able to work with these. And and you're not to the memorization part of it yet, just the working one. These fundamental identities need to be added to your sheet. Okay. So, what happens if I want to find the exact value of a trig function? Okay. Tangent of 20 minus the sine of 20 over the cosine of 20. Okay. Now these are looking flat out ugly, ain't they? But they are deceptively simple. So, what is tangent? Tangent, sine over cosine. So what I'm going to do here, instead of writing tangent 20 minus that, I could write either sine 20 over cosine 20, or I could take tangent of 20 minus tangent of 20. What do I get? 0. Simple substitution. Now, we got sine and secant, okay? So secant is the same as 1 over cosine. Okay? So if I see something that's secant, I could switch that over into cosine, right? We always want to try and work with sine and cosine as much as we possibly can. So I could rewrite this instead of the secant, I could write this as cosine squared of pi over 12, correct? but this would be 1 over that, right? So that means we're going to have to flip it up and use it as a reciprocal. So that means it's going to be sine squared pi over 12 plus cosine squared pi over 12, which is equal to what? 1. Why? Sine squared plus cosine squared is equal to 1. So because this whole piece here is the same as secant, multiply by its reciprocal and away you go. A lot of mental gymnastics with it, but it's not that big of a deal. Now, mind you, you can go and solve for it, but keep in mind here that whenever you take the square root to both sides of an equation, you're going to get plus and minus on here. So, take a look at this. Okay, given that sine of theta is equal to 1/3. Now, we're supposed to go through and find the rest of the stuff, right? What I suggest, okay, set this up. This is A, B, C, okay? Now, another way of thinking about this is, again, our right angle is here. This is going to be our theta. This is going to be opposite. This is going to be adjacent. And this is going to be hypotenuse, correct? So, if I am given that the tangent of theta is equal to 1/3, that means tangent of theta is opposite over hypotenuse, correct? So that means that this value here is going to be 1. This value here is going to be 3. What's got to be here for the side adjacent? Well, that would end up being 3 squared is 9, minus 1, which is 8, correct? Square root of 8, because we got to deal with the square root of that, is going to end up being 2 square root 2, correct? Because that's going to be 4 times 2. Take the square root of that, so we get 2 square root 2. Now I have everything else. So when I want to do cosine, which is what? Adjacent over hypotenuse? So that is going to be equal to adjacent, which is 2 square root 2. I said 2 square root 2 over 3. Okay. So now mind you, it says cosine has to be less than 0. So if I go back here, cosine less than 0 only exists where? Cosine is the x, so that means where is x negative? That means it's got to be over here in one of these two possibilities, right? Now, it also said that sine was what? Sine was positive. And if the sine is positive, that means it's in the second quadrant and first quadrants, correct? Because sine is y. So which quadrant is this thing going to be coming out of? This has got to be coming out of quadrant 2. So head back over here. Okay. So we know that this is going to have to be negative, correct? This just identifies what its distance is going to be. That's all that it's doing here. So this is going to be negative square root 2 over 2. So what about tangent? Tangent is sine over cosine, or in this case, opposite over adjacent. So we said that this was negative here, correct? So that's going to be negative 2 square root 2 over 3, correct? So now I want to find the rest of them. Well, cotangent, well, that's going to be equal to negative 3 over 2 square root 2, which means that I'm going to end up having 3 square root 2 over 4. The square root of 2 times the square root of 2 is 2. 2 times 2 is 4. So now we've got secant, which is the reciprocal of cosine. So this is going to be negative 3 over, yeah, the cosine, did I mess up on that? Yes, I did. It was supposed to be opposite, right? Why didn't you catch that there, sir? TOA, opposite over adjacent. Opposite, 1, adjacent, 2, square root 2, which means that this thing is going to end up being the square root 2 over 4. You're supposed to catch those things, guys. Tangent, opposite over adjacent. And I started doing that because I was talking negative. Terrible. So cotangent is still going to be negative, but it's going to be the reciprocal of that, which is going to be 2 square root 2. Secant, reciprocal of that, which is going to be negative 2 square root 2, which would end up being 3 square root 2 over 4. Cosecant is the reciprocal of sine, which is simply going to be 3. Easy enough? It is a great amount of mental gymnastics on this stuff. But I have always found that it goes and helps out to have this in here to identify what all your values are going to be. Then if they tell you something like this, whether or not it has to be greater than 0 or less than 0, will tell you where things are going to be, what's going to be positive, what's going to be negative. Okay? So, let's see. Just to double check since I was messing up on those things. Yep, good deal. So, finding the values of a circle of radius r. Information there. Like I said, I tend to use a right triangle on it so that I don't have to worry about Pythagorean theorem, even though I do use that in there. I like having it written out with the triangle, so I got my opposite and adjacent and going back to SOHCAHTOA. For me, it's a lot quicker and easier, and it's less prone to error unless I'm writing down the wrong numbers. So then, let's see. Let's see what else do I want to do here. Odd and even properties. You've kind of picked up on this from the unit circle itself, where we got sine of negative theta is equal to negative sine of theta. You should have noticed these things, that we have a certain level of a repeating pattern here. So, say for example that I am looking at, let's pick a number here once real quick. I want negative sine of 45. So if I am going to do the negative 45 degrees, negative 45 degrees means I'm going to go down here. So the sine turns out to be negative square root 2 over 2. Well, what's the sine of square root 2 over 2? Well, the sine of 45 degrees, square root 2 over 2. But you put a negative in front of it, and you get right to what we're talking about. Negative theta and negative of the theta. Odd and even properties. Again, have it written down so that you have access to it. There are a great number of these properties that are out there, and you have to have them written down so that you've got your reference going back and forth with them. So I'm going to let you get to work on this, and we'll take care of questions as they come.